Hello, I welcome you all to this channel again. In this particular video, we'll be looking at some aspects of oxidation states of lanthanoids and lanthanoid contraction. So before you watch this video, so I request you to watch my previous video on the concepts of lanthanoid, where electronic configuration of lanthanoid has been described, and even a trick to remember lanthanoid series and their writing electronic configuration, trick to write electronic configuration, that has been described, right? So as a continuation of that video, we shall see oxidation states and lanthanoid contraction in this particular video. So before I begin with this, so this slide was there in my previous video also. One point I wanted to just make clear. So actinoids, in general, actinoids, they are represented as AN. By mistake, it was AC in the previous video. Please rectify or please note this mistake. So if I write AC, that represents actinoid itself, the element actinoid itself. AN, it is general representation of actinoids. Fine. So in my previous video, so what were lanthanoids, what were actinoids, that one, and then next how to write their electronic configuration and how to remember the names of lanthanoids, all those things they were described, right? So now go ahead with oxidation states. Oxidation states of lanthanoids, if you consider, the most common oxidation state, it is 3 plus oxidation state. All lanthanoid elements, they can exist in this 3 plus oxidation state, which can be in general represented as Ln 3 plus. So in solution state, definitely this is most common oxidation state. So along with this, some other oxidation states are also there. Of course, variety of oxidation states are possible, but in that, most common is this, and other most important oxidation states, they are 2 plus and 4 plus. Now 2 plus oxidation state in case of lanthanoids, it will be shown by europium as well as ytterbium, right? So now to understand why this europium as well as ytterbium, it can show 2 plus oxidation state, again we should go back to their electronic configuration. So now by now I hope you know how to write the electronic configuration of europium. So if you can recall the electronic configuration, ground state electronic configuration of europium, it will be 4f7 and it will be 6s2, right? So in 2 plus oxidation state, we will be just removing 2 electrons from 6s. That leaves the system as f7. 4f7 will remain. 4f7 being exactly half filled, europium, it can show an oxidation state of 2 plus, right? For similar reasons, ytterbium, it can show oxidation state of 2 plus. Ytterbium ground state electronic configuration, if you remember, it will be 4f14 6s2. In 2 plus oxidation state, again 2 6s electrons, they will be removed, and we are left with 4f14. So here I have not written 4, but it is understood that it is 4. So this leaves ytterbium 2 plus in f14 configuration, which is fully filled configuration, which is having more exchange energy, because of which it is stable, and that's how this 2 plus oxidation state, it can be exhibited along with 3 plus oxidation state for these two elements. Definitely these two elements, they will show the general or common oxidation state of 3 plus, but along with that they even show 2 plus oxidation state. Similarly, there are two more elements which can show an oxidation state of 4 plus, right? Among the elements or between the elements which show 4 plus oxidation state, very important one which should not be forgotten is this cerium, which can exist in 4 plus oxidation state. Again, why it can show 4 plus oxidation state? Go back to its electronic configuration. Ground state electronic configuration of cerium, it will be 4f1 5d1 6s2. If we make it in 4 plus oxidation state, or if we take it to 4 plus oxidation state, all the 4s electrons, which are 6s electrons, 5d electrons, and 1 4f electrons, so all these 4 electrons, they will be removed. This makes the system f0, completely empty f subshell, which will be more stable, because of which cerium, it can exist in 4 plus oxidation state, right? Similarly, this element, it is terbium. This can also exist in 4 plus oxidation state, because when it attains 4 plus oxidation state, it will be left with 4f7 configuration, right? So 4 plus for 2 elements and 2 plus for 2 elements. This should be remembered, right? Terbium, okay, even if we do not remember, it's of not that use, but these three, europium 2 plus and cerium 4 plus, definitely they are very important. Okay, why they are important? It's because of this reason. Cerium 4 plus, it can be even represented in stock notation in this way. Cerium 4 plus, it is very good oxidizing agent. In fact, even it can oxidize water because of kinetic reasons. Usually that oxidation, it will not be observed in solutions, but cerium 4 plus, it's a good oxidizing agent. easily you can understand now. Cerium, it is in 4 plus oxidation state. So it can be converted to 3 plus oxidation state. So cerium 4, when it comes to cerium 3 plus, it will accept electron from some other species. Therefore, the other species, it gets oxidized, and that's how this cerium 4 plus, it is an oxidizing agent. Right? If you want the basics of oxidation reduction, for on that also one particular video I have made, that I have briefly explained all these aspects. So probably title of that video is coordination complexes as redox agents or something like that. Please you can watch that video where all these concepts of oxidizing agent, reducing agent, all these basic aspects are nicely explained. Fine. Cerium 4 plus, it can come back to cerium 3 plus, because cerium can even exist in 3 plus oxidation state. So therefore 4 plus to 3 plus, it accepts electron and it can act as oxidizing agent. Similarly, europium 2 plus, if you consider, europium, it can undergo oxidation from europium 2 plus to europium 3 plus. Europium, it can change its oxidation state from 2 plus to 3 plus, which means that it is losing an electron. Europium 2 plus, it is losing an electron, or it is donating electrons to some other species. In turn, the other species which is accepting electron from europium 2 plus, it gets reduced, and therefore this europium 2 plus, it can act as a reducing agent, right? So therefore europium, it can exist in 2 plus oxidation state, that is important, and cerium, it can exist in 4 plus oxidation state, so that's also important. So these are briefly some important aspects of oxidation states. Now, a third thing that we can look in connection with lanthanoid series is their atomic and ionic radii. Atomic and ionic radius, at first point what I can say is that it's not much different for all lanthanoids. It's almost similar for all lanthanoids, whether it is atomic radius or ionic radius. There is no much difference. Say from you start from lanthanum and you go up to lutetium, almost they are similar. But what you can notice is atomic as well as ionic radius, it decreases steadily along the period or series. What I mean to say is, if I start from, say, I start from lanthanum, right? And then lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, I just continue up to lutetium. If I monitor the atomic radius, it gradually, uniformly, steadily it decreases. In fact, this gradual decrease, it is more prominent in ionic radius than in case of atomic radius. So lanthanum 3 plus to lutetium 3 plus, if you consider, gradually size it goes on decreasing. Fine. Always exceptions should be remembered. Exception to this fact is that the atomic radius of europium and ytterbium. So these two elements, they can show 2 plus oxidation state. We had met these two species in oxidation states, the earlier property, right? So these two, they have slightly more atomic radius than this gradual trend, whatever is expected. So from that gradual trend, slight deviation is observed in case of these two elements, and that is because of again their electronic configuration is responsible for that. So this is 4f7, all f orbitals exactly half filled, which causes electron repulsion, and that slightly contributes to the size, or slightly it increases the size of the atom. Similarly here, all f orbitals, they are completely filled, because of which ytterbium, it has got slightly more size than expected. Except these two, it is steady decrease in size, right? First point, size, it is comparable, very much similar. But if you just notice the change, it is slight decrease or gradual decrease, steady decrease from lanthanum to lutetium. And this fact, steady decrease in size, that is always or sometimes that can be called as lanthanoid contraction. So lanthanoid contraction means usually this steady decrease in size of lanthanoids when we move from lanthanum to lutetium. This is very, very important in connection with lanthanoids, right? And what is the reason for this lanthanoid contraction, and what are the consequences because of this lanthanoid contraction? How properties of lanthanum to lutetium, it gradually changes. That fact should be looked. First thing what we can look at is cause. So simple words, in very simple statement, if at all have to say, I can say that in one sentence or one phrase, this lanthanoid contraction, it is because of improper shielding of 4f electrons. So this improper shielding of 4f electrons, that results in steady increase in effective nuclear charge when we move along the series. And when effective nuclear charge or Z effective increases along the series, size also decreases. Right? So we can look into this fact in more detail with an example, or when we go to consequences there we shall see this improper shielding, its meaning, and how exactly it results in lanthanoid contraction. All those things we shall understand consequences. Okay, first consequence, very important consequence, is this. It's because of lanthanoid contraction. Similarity in atomic sizes in 4D and 5D series. Usually if we go down the group, in any group, atomic radius it increases. So same thing it is expected for from in transition metals too. Say we are moving from 3D to 4D or 4D to 5D we are moving, right? Even for that matter, even we can move from 5D to 6D, but let us consider this example, this illustration. 3D to 4D if we move, say one particular example for that which I have taken is titanium to zirconium. Titanium, zirconium, hafnium, correspondingly 3D, 4D and 5D series elements. So down the group if we move from titanium to zirconium, you can definitely find the increase in size of titanium. It is 132 picometers. When we move to zirconium, 160 picometers, it has increased, and this is general trend, it is expected. But now when we move from 4D to 5D or zirconium to hafnium, this is the most cited example, and that's how I have taken this example itself for lanthanoid contraction. Zirconium and hafnium, they have got almost similar size, 160 picometers, 159 picometers, almost similar size, right? Expected thing, even when we move from 4D to 5D, there should have been increase in size. Here, say at least by some 28 picometer increase we find. Similarly, some increase we could have expected, but they have got similar size. And reason behind this is straight away said to be lanthanoid contraction. How this lanthanoid contraction is, or how because of lanthanoid contraction this is observed, that we should see. Right. See, when we are moving from 4D to 5D, after 4D, and when we are entering into 5D, we fill so many electrons in between. Say zirconium to hafnium we are moving. When we are moving from zirconium to hafnium, we are moving from 4D to 5D. We will fill so many electrons or so many shells are the subshells are there between this 4D and 5D subshell. Those shells or those subshells, they take electrons. And now here if you consider major electrons or 14 electrons, when we are moving from zirconium to hafnium, they go into 4F subshell, right? 4F electrons are filled gradually when we are moving from 4D to 5D. Now, these 4F electrons, they do not cause proper shielding. To understand this, you can understand or you can you can look at this diagram. So here this is a rough sketch to explain the phenomenon. Let us say these are 5D electrons, or 5D electrons we are adding it here, and 4D electrons they were added here. So when we are moving from one element to other element, or when we are moving from 4D to 5D series, right? So what we do is the elements which come in between, in that case, major electrons they occupy this 4F subshell. Now imagine if this 4F subshell, if it had acted as a screen, good screen to nuclear charge over this 5D electrons, right? So this itself is known as screening effect. So these are outer electrons. These inner electrons, they start acting as a screen to this nuclear charge over these outer electrons. If these inner electrons, they act as a screen, nucleus, it cannot take good control over these outer electrons. If nucleus, it is not taking good control over outer electrons, the size of the atom increases. This is usual trend. Now, but in this case, what has happened is these 4F electrons, they are not good screening agents, or in other words, they are causing improper shielding. If they had caused proper shielding, then again what could have happened? Because of addition of this 4F electrons before we fill 5D, because of 4F electrons, these 4F electrons, they would have acted good shield or good screen to nuclear charge over this, because of which nuclear charge is screened over this 5D electrons, and size, nucleus, it loses control over 5D electrons, size it would have increased. But now this 4F electrons or F electrons, they are not good screening agents, because of which these 4F electrons, they cause improper shielding. Because they are causing improper shielding, nucleus, it can take control over outer electrons easily, right? Because of which size of the atom it decreases, or in other words, what I can say is expected increase in atomic radius that will not be observed. and this itself is this is itself is exactly what is the shielding effect and how this 4F causes improper shielding effect. Same thing, right? And this being the important reason for the similarity in size between zirconium and hafnium. This is first consequence. Usually this will be taken as important consequence of lanthanoid contraction. Next, second thing, this gradual decrease in size, it changes so many properties. Gradual, it brings so many, it brings changes in so many other chemical properties of lanthanoid compounds. Mainly, you can consider decrease in basic strength of hydroxides and oxides. Of course, when you can consider oxalates, citrates and all, but important compounds are lanthanum hydroxides and lanthanum oxides. So when you move from say lanthanum hydroxide to lutetium hydroxide, so lanthanum hydroxide, because of this hydroxide group, you can think that in aqueous solution it can act as base. If we move from lanthanum hydroxide to lutetium hydroxide, the basic strength, it is found to be decreasing. So lutetium hydroxide, it is least basic among these lanthanoids, and lanthanum hydroxide, you can consider it to be most basic, right? So very simple thing, you can understand it in terms of size of cations itself. So here lanthanum comparably it has got larger size. When we move along this series, lutetium 3 plus, it will have minimum size, though they are comparable. Comparatively, lutetium 3 plus, it has got minimum size. Now because of minimum size, charge density on lutetium it increases, and that increases covalent character between lutetium ion and hydroxide ion. Or because of this higher charge density, hydroxides, they prefer to be attached to this lutetium 3 plus itself, and they will not get released to aqueous solution that easily as compared to that of lanthanum hydroxide. Therefore, you can think that lanthanum hydroxide to be more basic, lutetium hydroxide to be least basic among these species. And when you move along this series, basic strength, as I have mentioned earlier, it decreases. So if I say basicity or basic strength, it decreases along this series, the other thing that readily follows is acidic strength, it increases in this direction. So this is most basic, this is least basic, whereas acidic character point of view, acidic strength point of view, right, the one which is least basic, that is this, that should be most acidic. So acidic and basic properties, if you consider them to be reverse of each other, basic strength decreases in this direction, acidic strength it increases in this direction. This is most acidic, this is least acidic, right? So about this covalent and ionic character at the beginning itself I have mentioned. So slightly covalent character it increases in this direction, because of which you can even expect solubility decrease when you are moving from this to this. Solubility it also decreases, aqueous solubility. It is because covalent character it increases in this direction, right? If I say covalent character it increases in this direction, in other words, it can be even said that ionic character decreases in this direction, right? So these are some other properties. Mainly they are based on a decrease in basic strength of hydroxides and oxides. Next consequence, difficulty in separation. So lanthanide compounds, earlier it was very difficult to separate them, and the reason behind this was that lanthanoids, they are difficult to separate due to similarity in size and charge. As I have mentioned, though size varies, sizes of all lanthanoid ions, they are not much different, they are comparable. Charge wise, all usually they will have 3 plus charge, right? So because of this similar charge and similar size, their chemical behavior it goes similar, and when chemical properties are similar, definitely it goes difficult to separate them. So usually earlier methods they involved separation of these lanthanoids in the form of fractional crystallization, fractional precipitation. Some tedious methods were followed, right? Some keeping some competitive, advanced competitive exams in mind, I am just mentioning this fact. Nowadays it will be separated easily, or with ease. Lanthanoids they can be separated by something called as ion exchange chromatography. So in this ion exchange chromatography, what they do is, so they take something called as, say, this will be, you can call it as column, right? So here there will be some ion exchange resin, it will be filled, and now here above the mixture of lanthanoid compounds that will be added, and now from above some complexing agent. There are different examples available for even resin. So many examples are available here. Complexing agent like citrate ions, as eluent it can be added. Eluent means it is the compound which moves along the column. So eluent, complexing agent, it will be added. Now when you go on adding this, what you can expect is smallest cation among this mixture. So according to lanthanoid contraction, we know lutetium 3 plus, it is smallest cation. That smallest cation, it forms complex readily or more easily, right? And that complex, it starts coming along with this complexing agent. Complexing agent, it readily binds smallest cation and it starts coming out. And so now, so if you repeat this process by taking a long column for a long time, so what you can expect is all lutetium ions, lutetium 3 plus ions, they form complex first and they start eluting first. They come first out of the column, right? And if you continue the process, then slowly one by one, next smallest cation, one by one, they start coming out. In this way, in the form of complex, you can separate this lanthanoid ions, right? So first, as I said, smallest cation, it is lutetium 3 plus, then next, and ultimately at the end you can expect lanthanum 3 plus. So it is because of its small, because of its larger size, this is smallest, larger size, its complexing is ability, it will be less, and therefore it will form, it starts forming complex at the end, and because of which it comes in the end, right? So this is about lanthanoid contraction and its okay, let us look at some previously appeared questions on this oxidation states, electronic configuration, and lanthanoid contraction and all. So first one simple question from JEE 2002. The correct increasing order of ionic radii. So four options they have given. Increasing order of ionic radii they are asking. The basic fact that you should know to answer this question is about lanthanoid contraction. See, in case of lanthanoids, 4F series, if you go from say lanthanum to lutetium, of course all these are in 3 plus oxidation state, you know there is steady decrease in size. So lanthanum to lutetium, there is steady decrease in size. Now, if lanthanum to lutetium, if there is steady decrease, lutetium it should have smallest and lanthanum it should have maximum size. So just if you look at this fact that lanthanum or lanthanum 3 plus ion, it should have highest size. So you have two options here. So one among this, one between this, that can be the answer, right? So now the second one, if you look at, so now lanthanum, after that directly you will get cerium. So cerium it should have little less size than lanthanum 3 plus, which means cerium it is expected at this end, but cerium they have placed it at this end. So just based on this you can conclude that this should be the answer. And even if you look at the order and lanthanum, cerium, praseodymium, neodymium, it continues like that. Last will be ytterbium. So lanthanum, cerium, praseodymium. So it's in correct order itself. So therefore this option A should be the correct answer for this question. Okay, let us go to the next question. Next question. The most common oxidation state of cerium are, this we know, +3 is very common oxidation state and it is shown by all lanthanoids. In addition to that, the element cerium, it shows +4 oxidation too, and this +4 oxidation it is because of the fact that it can attain F0 configuration, so which will be stable. Therefore +3 and +4 both are possible for cerium. So option 3 should be the answer for this question. Next one. Lanthanum 3 plus ion, this is interesting question. Lanthanum 3 plus ion, its radius is given to be 1.06 angstrom. What is the radius of lutetium 3 plus? In brief, I have written the question. It's also from JEE examination itself. Now, definitely you will not be remembering this, what is the atomic or ionic radius of lanthanum 3 plus, what is the atomic or ionic, in this case particularly ionic radius of lutetium 3 plus, all this atomic or ionic radius we will not be remembering. But definitely they have not asked this question on that fact. Just we should know the fact that when we move from lanthanum to lutetium in this direction, there is steady decrease. So if lanthanum 3 plus it is 1.06 angstrom, lutetium 3 plus obviously it should be smaller than that. That is the thing that is the question is expecting from you. See, now look at the options. 1.60, which is larger than this cannot be the answer. 1.40 larger than this. Third one exactly same size. No, because lanthanum 3 plus to lutetium 3 plus there is steady decrease in size. We are just left with option 4, and therefore answer for this question, it should be 0.85 angstrom, which is lesser than lanthanum, 1.06 angstrom unit lanthanum 3 plus. So therefore that should be the answer. Fine. Consider one more last question. This is Identify the incorrect statement. 4 statements they have given. So among this, which is incorrect? This is very important whenever this kind of questions are asked. So there are all chances that we can go wrong, because when incorrect statement is to be identified, other 3 statements, if it is single correct answer type question, definitely other 3 statements they will be right. So by chance, if we mistake that they are asking about the correct statement, there are all chances that we can mark some statement, or say just if we look at the first option, there are all chances that maximum chances that first statement will be right, and if we confuse that they are asking about right statement, you may just mark 1. So in that way, there are all chances with this kind of questions that you can go wrong. So you should be very careful. Okay, now let us look at the statements one by one. So first one, lanthanoids, the other term is lanthanons, are reactive than aluminium. Okay, about this statement, let us say we do not know anything. So in this kind of questions, even if we do not know everything, it is possible to answer. Let us not bother about this first statement at this stage, right? So let us just keep this first statement aside. Let us go ahead with the second statement. Cerium in its 4 plus solution, it is used as oxidizing agent, and this is a very important fact that cerium 4 plus, it can act as oxidizing agent, and in many volumetric analysis, many titrations are there using cerium 4 plus as a reagent. So therefore this is obviously correct statement. Next, europium 2 plus, europium shows 2 plus oxidation state. This is also fact, because of 4f7 configuration, it is possible for europium to attain 2 plus oxidation state in addition to 3 plus. So therefore this statement, this should also be correct statement. Option 3 is also correct statement. Then option 4, if you look at basicity decreases from say it's promethium to lutetium, right? So therefore size decreases, and because of size, in fact they are talking about basicity of corresponding oxides and hydroxides, and so even if they just say it is promethium to lutetium, you can understand that you can consider them to be the hydroxides or oxides, nothing wrong. So yeah, promethium to promethium, it's not promethium. Even in previous slide, I think have wrongly mentioned it to be promethium. So I think this is praseodymium, and PM it is promethium. Fine. Now praseodymium to lutetium, right? It is size there is decrease, and because of size decrease, you can find basicity decrease. So therefore even this statement, statement number 4, it is correct itself. So now even if we do not know about the first statement, that whether the first statement is correct or not, we can conclude that because other 3 statements they are right, so this should be wrong statement, and your answer, this is your answer, because they have asked you to identify incorrect statement, and incorrect statement is this should be the answer. So these were a few questions related to lanthanoids, and lanthanoids and actinoids. If we consider actinoids, much chemistry is not known, so less questions are expected. If we are prepared well for lanthanoids, it's more than sufficient. Thank you for watching this video. So hope this has helped you. This video, it has helped you. If you like this video, you can just give a like, and if you have not subscribed, please do subscribe to this channel, and you can recommend this channel to others. Thank you again.